Hey, Tees, how's it going? Mr. Cortez here for your second Zoom on Unit 4. So this is your last Zoom for this module. Hey guys, thanks for joining in. Let's make sure everybody gets in. How's everyone doing tonight? Cool background, Mr. Le, the planet thing. I like that.
Get them all. We'll get all and all from the front.
All right, just wait a couple more seconds. Make sure everybody gets a chance to join in. Remember, today is the last day of this module, so please try your best to turn in all homework, basically. Today at midnight, you'll be switched, so you won't have access to this module anymore. So definitely try your best to turn as much as you can in to get that grade up pretty good. On Monday, just a reminder, Monday we don't have Zoom, we don't have lab, we don't have nothing. Right? You guys are off. It's Memorial Day. Excuse me. So sorry, I didn't want to cough into the mic. So on Monday, Monday we're completely off, right? You guys have a day off, so please enjoy yourselves, spend time with family, go to the beach. Hopefully it'll be nice and warm. That's for sure what I'm gonna try and do if it's warm. I typically for Memorial Day weekend, I always go to this festival in Maryland. It's a metal festival, but we won't get to do it this year. I'm a little too busy. But I'll still enjoy it. Probably go to the beach if it's nice. And it's important to take time off, and get your mind off of school and work for some time. It's important to enjoy yourselves. Enjoy life. That's why we are learning. That's why you guys are going to school. That's why all this stuff, all this trouble you're going through to better your lives is to enjoy life. So just always remember that's really important to keep that up, keep yourself happy. But always having focus, right? Always having a goal. So that's pretty important. So. And luckily we live, in such a beautiful city. No matter how expensive it gets in San Diego, I don't think I'll ever leave, and I've lived in many, many different parts of the country. I've lived in Maryland, I lived in Virginia, I lived in LA. Um, San Diego by far is the most beautiful city. It's got everything. It's also one of the most expensive cities, but good things come with a price. So well, luckily we're in a trade that, we're fortunate enough where, um, you can definitely make some money and you can have a rather comfortable life. Um, so keep up with the training, keep up with the study, and it will pay off. It will pay off. So, all right. So today, what we're going to go over is the last couple topics related to residential. So, on our last Zoom, I kind of left off on the voltage drop topic. So, we're going to start with that, focusing on that. And then if we have any remaining time, we'll go over some of the other things. I'm going to skip this whole load center calculation thing. Again, it's kind of a random, I don't know. I've never seen that put to use. I don't know its utility. So I'm not even going to go over that. But the voltage drop, that is absolutely crucial. That is something that for sure is a factor and for sure is important for electricians to know, right? This other stuff that I'm seeing here, some of it is important and relevant. Um, Mostly like let's see, oop, sorry. So a lot of the stuff we did go over, right? The calculation, the residential calculation. Um, but probably just like a more like a recap of some of that stuff. But I'll go over it if we have time. And basically, it's excuse me, it's just really leading up to this form, right? Which is the calculation form, right? The square footage times 3, the 2 kitchen small appliance, the 1 laundry appliance circuit, calculating all that, getting 35%, or I should say 100% of the first 3,000, 35% of the remaining amount, getting your fixed appliance loads, then calculating your range, your dryer, heat, getting all that stuff. So I might go further into detail as far as maybe after we get our total wattage, after we get our amperage. I'll go into how to, from that amperage, select a main breaker size, also select the proper wire size, and then also select a uh, size grounding electrode conductor, right? So what that is the wire that's connecting our electrode, which is our copper rod, in a home, establishes the ground to our main panel, right? That's called a grounding electrode conductor. So show you guys how to do that. And we base that off of the total amperage in the main breaker. So I'll show you where we get that in the NEC. I'll also go over, this is also relevant and important, is selecting the neutral conductor. So we are not going to quite use the same size wire for our hots, excuse me, coming in for our service entrance. Same size wire for the neutral, and I'll explain why. And so we're actually able to pick a smaller wire for the neutral. And I'll show you guys why. I'll teach you why and how to go about that. So, all right. But again, our main focus right now is going to be voltage drop. And so, voltage drop. So let's see here. The size of a conductor required to connect an electrical load to the source of supply is determined by several factors, including the load current in amperes, the permissible voltage drop between source and load, total length of conductor, and the type of wire. So, in a simpler way to understand this is what this is saying is that we have to factor in a couple of different things when selecting a wire size. Right? One is how much amperage the load, right? And again, whenever I say load, that could be a motor, it could be a light, it could be a compressor, it could be a pump, right? Anything that's using electricity is a load, right? So that load determines how much amperage it's going to need, right? That's what basically dictates the amperage needed from the panel, right? So if a motor is 40 amps, 40 amps are going to be pulled. If a motor is 10 amps, 10 amps are going to be pulled, right? So the load, the type of load determines how much amperage it's going to need. Another factor is voltage drop, right? So again, what that means is when you have too long of a distance between your source and your load, the conductors themselves become a type of load where they're using some of the electricity, and how it's reflected is in heat, right? So the wires are hot, and the longer the runs are, you're going to drop some voltage on the wire itself, right? And so the danger of that is starting off from your source with a certain voltage and not end up delivering that voltage to your load, right? That's what voltage drop is. And I'll give you guys, again, some examples on how to do the math. Total length of the conductor, that's crucial. And the type of wire, copper and aluminum, right? Most of the time it's going to be copper for us. Sometimes we'll do aluminum, but I would say probably 80% is going to be copper. Okay, so right here, this is a kind of an example of where something like this would drop, or would you would see this. So this parking lot fixture has 3 1,000-watt lamps, is 300 feet from the panel, uses number 12 wire, and is supplied by a 20 amp 208-volt circuit. The fixture manufacturer, right, who made the lights, specifies a maximum voltage drop of 3%. Does this circuit adequately support the load, right? So what this 3% means is that you cannot have on this particular light, and 3% is a pretty standard voltage drop number. What this 3% means is that you cannot drop more than 3% of your, in this case, 208, right? So it can't be lower than 3%. And how to get 3% of anything? Show you real quick with the calculator, or how to get a percentage out of anything. Basically 208 times point 0.3. Nope, that's not it. 0.3. 208 times 0.03. So we cannot drop more than 6 volts, 6.25. So your voltage at these lights, if you subtract 6.25 from 208, 6.25 from 208, so your voltage cannot be lower than 204 volts. Because if it's lower, then these lights will not operate correctly, right? So that's what voltage drop in that percentage means, right? So again, 3% is a pretty general number for voltage drop. The only other percentage that we go off of is when it comes to feeders, right? And feeders are when you have a wire from a panel to a panel, right? That percentage drop is 5%. So you're allowed to drop more in a feeder. But in branch circuits, and again, branch circuits are from an overcurrent protection device, such as a breaker or a fuse, to your load, you cannot drop more than 3%, right? So in the 208, you can't be lower than 204 volts. If it's 120 volts, you would get 120 times 0.03. So you can't drop more than 3.6 volts. So you can't be 3.6 minus 120. So your voltage can't be lower than 116 after the voltage drop. Okay, so again, it can't be lower than that. So that's what voltage drop is, right? So we're going to figure out how this works. So here I have an example. And here I just made up some random, it's a random scenario. Your voltage source is 240, let's say. And let's say you got a really long conduit run, or it could be PVC, it could be EMT, it could be rigid, whatever it is, but you got a raceway that's 250 feet away from your source. And you have a motor that needs 40 amps, right? So those are the parameters that we're going to work with. Their source voltage, the length of the run, the load, and the amperage the load needs, right? So with voltage drop, there is a formula that we have to memorize. And I don't like teaching to memorize formulas, right? Again, if I've taught you Ohm's law, right? I've taught you the trick of using Ohm's law wheel or the circle. And again, there's no need to unnecessarily remember formulas if we can find a way around it and still be accurate, right? But with this voltage drop thing, there's no way around it. We have to just know this formula, right? And again, I like making things simple and easy to remember. So the formula that I remember for voltage drop is 2 kil over Cm, right? It's kind of easy to remember 2 kil, So 2 times K times I times L over Cm, right? Remember, just 2 kil over Cm. That's the formula, that the voltage drop formula. Now, there's other voltage drop formulas, but I like going off of this one. And I'm going to show you, I'm going to teach you guys this one. And this is the one I've used. And you will see these types of questions in your journeyman's exam for sure. There's going to be voltage drop questions. And knowing this formula will be able to get you the correct answers, right? So explain what each one of these things means. So what 2 is for the conductors, right? Because you have a hot going there and you have a return path back to source, right? In a 240, it's going to be 2 wires, 2 hot wires, right? So with this is even though we don't have a neutral, one of the hots acts as where they're delivering current, and the other one acts kind of like a neutral, except that it's a lot faster because you're pulling from the two phases. So same concept, you need a complete cycle, right? So that's why we have two, because you have one way of the current going there, you have to have that current going back. So that's why we have the two. When it comes to three phase, this changes and it becomes 1.73, right? But I'll explain that in the commercial one. The rest of the formula is the same. That's the only thing that changes in a three-phase system, right? This is for a single phase system. So whether it be 120 or 240, you're going to use two, right? These x's are multiplication, right? Times 2 times k times I times L. Okay, so what k is going to be a constant number, a multiplier, right? So if it's copper, the number is 12.9 if it's copper. If it's aluminum, it's 23.7. Now, where we get these numbers is going to be calculated through the code book. So the code book all the way in the back on chapter 9, table 8, this table is what we're going to use for voltage drop, right? So this is a fairly big table. There's a lot of things going on here. But essentially, that constant we get by dividing the first. Let me explain like this table so you guys can kind of get familiar with it. I know it seems like it's a lot of stuff in here and it seems a little overwhelming, but I'll break it down easy for you guys. So let me go ahead and grab this real quick and paste it up here so we can go over this stuff here, what all this means. So right here, this table is kind of split down the middle, like conductors and direct current resistance. And let me see here. Conductors and direct current resistance, right? So right here in the copper, what this table is basically is telling us based on the wire size, right? And this is what these numbers on the far left are. Wire size, you can see 18 all the way to 400 or 500 kc mil. Depending on the wire size, if you were to send direct current resistance, or I'm sorry, direct current, right? The internal resistance in copper, right? Even though copper is a great conductor, it still has some resistance in it, right? There's nothing in existence. I think, yeah, there's nothing really in existence that's a pure conductor that will have zero resistance. Now we have some things that are close. There's a new type of material called a superconductor, and that's very brand new stuff. And a superconductor, what that is a material that's frozen to an extreme temperature, and that closely resembles zero resistance, right? And we don't use that. Where that's being used, I don't know if any of you guys have heard of what quantum computing is. So, it's been kind of a new thing in the last month or so, but it's not really super new. Scientists have been trying to figure out quantum computing, and it's pretty mind-blowing what it is. Basically, when you get a material and make it a superconductor, so you freeze it artificially to like an insane cold temperature, what happens inside that material, and I know it sounds like science fiction or it sounds like a movie, but what happens with that superconductor is that it actually starts to like the electrons start to shift in and out of like parallel dimensions. And so what quantum computing is basically instead of what first off, let me explain like regular computing is like in a PC and a motherboard. And I don't want to get too crazy into that because I still want to stay on topic, but what regular computing does, it just operates off of current, right? Very low voltages and very small pulses of microamps going, you know, throughout the processor to your keyboard, to your mouse, to your monitor. That's all electricity, right? The processor itself is pulses of electricity being received from your keyboard, from your mouse, from video, and then it handles those currents and it makes processes, right? It says like, okay, yeah, he punched an A, and that's what A is. And when it display A, then he's going to type this up and enter, and we're going to process what that means, and then an outcome will come out. That's what a processor basically is, right? The problem with that, even though motherboards are made super efficient and it's very small amounts of current and voltage, there still is a heat problem, a heat issue where computers get hot, right? And that limits how much we can process, right? That's the limitations of computers, right? Before, those big computers that would take up an entire room to calculate 1 plus 1, they were just switches. Basically, they were relays operating to be able to hold electrically memory and calculate things, right? As technology has gotten better, we've gotten those relays smaller and smaller and microscopic, right? So but even if it's microscopic, we still have the problem of when you calculate a lot, it gets hot and that melts stuff, it degrades stuff. So what quantum computing is basically it's taking that same process, right? That you need a pulse, you need a signal, but instead of physically it being moved in conductors in processors, it makes calculations in an alternate parallel universe. I know it sounds crazy, but that's what it is. And so with the superconductor, when they freeze it, they take those pulses and it gets sent to another. Now, I don't know how that works, but I know that's how they do it. It gets sent to some alternate, like parallel universes, and it calculates at an incredibly fast speed without having to have that negative effect of the heat byproduct, you could call it. So that's why they're able to calculate so incredibly fast, is because they're sending those pulses and those calculations out to some other plane of reality or existence, which it can go incredibly fast, and it doesn't generate heat, right? And that's done through superconductors. So again, I don't want to get too crazy into that, but just thought it was really interesting. It kind of relates to what we're learning, right? So going back to topic, right, in a wire, there's always going to be some resistance. So even though copper is great, we send current, that resistance in the copper will generate heat, right? And that's basically voltage drop, right? The same issue that computers have on a small scale, we have it on a large scale, right? So what this direct current resistance is basically a study of, depending on the type of wire, whether it be uncoated or coated. And what that is not insulation. There's some wire that has a coating to it, and it's rarely used. So coated is not really something that we're going to get into. If it is aluminum, that's fine. I think aluminum does not come in coated or uncoated. And so what these numbers are based on the right here, there's two. There's kilo, the imperial system and the metric system, right? So we don't, this is America, we don't go off of the metric system. So basically, it's the ohms per 1,000 feet. What's the ohm resistance depending on the wire size? So in size number 18 wire, and why we have two entries of 18 wire, it's because it can come either in solid, 1 strand, or solid or stranded, 7 strands, right? Depending on if it's solid or stranded, every 1,000 feet, we're going to get 7.7 ohms of resistance, right? That's what these numbers are. So again, ignore like pretty much all this stuff here, and this is our numbers, right? So luckily, um, engineers and electricians have calculated a constant multiplier, which is way easier for us to use. So we don't have to worry too much about this number right here, but that's where we get these constant multipliers, right? So in the constant multiplier, is if it's copper, it's going to be 12.9. If it's aluminum, it's going to be 23.7. All right. So those again are just kind of numbers you have to memorize. Right? You have to kind of be familiar, write it down. But those are set numbers. That doesn't change. Right? Copper, 12.9, aluminum, 23.7. Right. So in this case, let's say it's going to be copper that we're going to be using. Right? So K would be 12.9. All right, that's what K is. Times I is going to be the current, right? So in this case, it's going to be 40 amps. So that's whatever amperage your load needs, 40 amps. And L is going to be the length, in this case, 250, right? So we take all those numbers and we replace those numbers with the variables here, right? So we're going to rewrite this. So we're going to say 2 times 12.9, and I'll get into what CM is. 12.9 times 40 times L. And in this case, L is 250 feet. 250 feet. And we got that division over CM, right? So what CM is circular mills. Circular mills. Okay, so circular mills, where we get that from, it's again all from the code book. If we go back to this table, and actually I have it right here. If we go back to this table, if you see right here, right, the wire size, right, you see area. And again, we don't go off of millimeters or anything like that. We go off of circular mills. So circular mills means the diameter of each wire. How much, it's a kind of a number of measurement of the thickness of the wire, you could call it, right? So that's what CM is, circular mills, right? So first off, how to approach this whole voltage drop problem is that first off, you're gonna first select a wire size that would work under any normal condition for this 40 amp load, right? So, and from that, when you then apply all these, when you apply this voltage drop formula, you're going to see that how much voltage actually will be delivered, right? So we're going to start off first by saying, okay, I got a 40 amp motor, right? And I want to see what size wire would normally fit in this. And here we're not going to factor in the ambient temperature. We're not going to factor in the more than 3 current carrying conductors. But if those situations were present, they would have to be factored in. Right? So just be aware of that. But just in order to simplify it, I'm not going to factor it in this particular example. Okay, so again, how to select what wire size depending on the amperage. And again, this is something that you guys should really start to really get down and really commit to memory. And again, it's going to be from the codebook, table 310.16. So wait a second for this to pull up. I'm going to go to 310.16. Right, remember, it's going to be this table here. And as you guys can see, I don't have that stuff memorized, right? I don't have exactly what 40 amp wire. Probably should, I guess, but why memorize it when you can just easily find it on the code book, right? There's certain things that you want your brain to be focused on, and certain things like why memorize when I can just easily get the reference, as long as you're aware and are solid in and then your accuracy and how to properly look up stuff. Why memorize things that you don't have to? Why add on to your brain something that's you can just easily look up, right? So again, for a 40 amp load, right, 50 amps or I'm sorry, 100 amps or less, we're going to pull from the 60-degree column. And so for 40 amps, let me zoom in here. For 40 amps, typically the size number 8 would do it. Size number 8 wire would do it, right? So we're going to go here and we're going to say, okay, size number 8 would normally, and let me put this in a different like color. Okay, we're going to say, okay, size number 8 typically would handle 40 amp load, right? So, but now we're going to put that size number 8 to test and apply this formula to that size number 8. Right, so how do we do that? Is that we're going to come back to this voltage drop table, you could call this. And right here, we're going to go down and come down to size number 8, right? And again, it depends if it's solid or stranded. Typically on size number 8, it's going to be stranded wire. So we're going to say, okay, size number 8, the CMs or circular mills is 16,510. So we're going to pop that 16,000 to 16 or 15? 16. 16,510. Boom. Okay, so now we got all our numbers filled out. Let's calculate all this stuff and see how much voltage we're dropping. All right, so right here, we're going to go equals. And so how we're going to handle this is first, we're going to multiply all the top numbers. Then once we get that number, then we're going to divide by the circular mills. All right, so we're going to grab our calculator. And again, when you take your journeyman's exam, you're going to have a basic calculator. So don't think I have to do this math manually or in a paper. As long as you're very careful with your decimal points, and as long as you're very careful with entering that information on there, you should be able to just do it with a calculator. And most things, you have to do it with a calculator, right? The calculation stuff. So don't, just try and do it by hand, and definitely don't try to do it in your head. Because again, you're going to be a little stressed. The test is stressful. And if you try to do it in your head, you might make a mistake, right? And you want to give yourself every opportunity possible to pass that test, right? So right here, 2 times 12.9 times 40 times 250. Right, and then so that's our when you multiply all these numbers, that's our final number, 258,000. And with that, we still have to divide by this CM. Right, so then we're going to divide by 16,510. And that gives us a voltage drop of 15.62. And here you can round it up. You can call it 16 volts. We're dropping, right? So in this example, so from the 240 volts, and we're going to subtract 240 minus 16, we're only delivering 224 volts with this current setup and this size wire. 224. Right? And remember that we cannot go lower than 3% on branch circuits. Right? And what's 3% of 240? Again, if you go here, 240 times 0.03, 7.2 volts. So if you subtract 7.2 volts from 240, so you can't go lower than 232. You can call it 233 volts. And we're delivering only 224. So then this size number 8 is too small. It's too small. The voltage drop is too much. We're exceeding our 3%. This wire is not gonna do. It's not gonna work. Right? Again, under normal conditions, if it wasn't such a great distance, it would be fine. Right? And I would say you only really want to start worrying about voltage drop if it's longer than like 100 feet. Right? If anything shorter than 100 feet, generally it's not going to be an issue. But if a run is longer than 100 feet, then you want to start thinking about some voltage drop calculations. Right? So now what happens? Oh, this wire is too small. So we're going to do the same numbers, right? Because that doesn't change, but we're going to select the next size wire up. And then after doing all the math, see if we're okay, if we're not lowering less than 3% of voltage drop. So size number 8 didn't work. Okay, what's the next size up? Size number 6. Size number 6, the CM is 26,240. So go back to this. Remember, those top numbers do not change. Number 6 is 26,240. 26, oops. 26 to 40. And we're gonna do the whole process again, but now with the new CM and see how much voltage we're dropping. And remember, we can't drop more than, I think it was 7.2 volts, right? And we were dropping 16 with that size number 8. So that's not working. So now we're gonna try it with size number 6. Oops, size number 6. And why again, size number 6? It's the next size wire up. So let's go ahead and do all the top calculations again. 2 times 12.9 times 40 times 250. Same number, 258,000 divided by, and why divided? Because whenever you see like a fraction type of thing, right, and we're trying to get one number, that really means that you can divide the top number by the bottom number and you'll get the one number that we want. So it's 26,240. And we're dropping 9.8 volts. Still, we're dropping two volts more than what we should. All right, so then size number 8 didn't work. I'm sorry, size number 6 did not work. So go the next size wire up, size number 4. And again, redo the whole thing, right? Because again, with size number 6, we're dropping 9.8 volts. And we can't drop more than 7.2 volts, which is the 3% for a 240 volt source. So right here, size number 4 is 41,740. So again, we redo the whole thing. Okay, 6 didn't work. So now we're going to go off of size number 4, 41,740. 41,740. And we'll do the whole thing again. All right, 2 times 12.9 times 40 times 250 divided by 41,740. Okay. Now we're only dropping 6.18. You call it 6.6 volts, right? 6 volts, that's fine. Because if you subtract 6 volts from the 240, right? And remember, we can't go lower than 224. 240 minus 6. So with size number 4, which is the one we ultimately ended up using, if we use size number 4, our voltage here, our motor, is going to end up being 234 volts. Fine, good, within the 3%, because we're only dropping 6 volts, and we can only drop up to 7.2 volts to our load. So that's basically the gist of it, is remembering this formula, 2 kil, right, over CM, and then getting your parameters, right, getting your if it's copper, which is generally going to be the case, getting your amperage, how much load your amperage is using, getting the length of the run from the source to the load. And then you want to start off by, excuse me, go to start off by just selecting a wire size that would typically work, and then applying this formula to it, and then seeing if you're exceeding the 3%. Right, again, we can't, and then it's not a whole lot, right? On 240, it's 7.2. On 120, it's 3.6 volts. So you really can't drop too much. So, and then if that doesn't work, just keep on selecting the next size wire up until a CM will fit and your voltage drop is not going to exceed that. Right? And that's the nut and bolts of it. That's pretty much the meat and potatoes of it, as it said. Voltage drop. Again, that's not something that the code book, there's almost zero mention of voltage drop in the code book. This table is more for like conductor properties, for other kind of stuff. But the code book isn't really concerned about voltage drop too much. And why? Because it's not really a fire issue, right? It's not like it's going to cause a fire if the machine doesn't operate, if the motor doesn't operate, if the lights don't turn on. The customer for sure will be upset, right? But the code book and inspectors, they don't really care. As long as it's not going to burn up, they don't really care. The only place I know where like the voltage drop is in the code book and is specifically like addressed and it has to be followed is going to be in pumps that operate sprinkler systems, right? Obviously, like if you don't factor voltage drop into a pump that's operating a sprinkler system that's connected to the fire alarm, and the motor doesn't work, when there's a fire, the motor won't pump and the motor won't activate and the pump won't keep on spewing water out. So for fire pumps, sprinkler pumps, that's I think the only place that I know. And there's probably going to be other places too, but the last place I really was like saw that voltage drop was mentioned in the code book is going to be for that, specifically for fire pumps. And again, it makes sense, right? You don't want to not factor in voltage drop in a fire pump, because it could mean that if there's a fire, no water will be spewed from the sprinkler system and the fire won't have any mitigation at all, right? It's just gonna, so other than that, it's not really a mandatory thing in the code book. But for us as electricians, as you working for a company, that is something that we definitely have to look out for, right? And you guys just saw what the calculation is. You can see it's not terribly difficult. It's just properly identifying key terms, knowing where to look, knowing the process, basically. That's the main thing. And if you use this formula, this process, whatever questions you'll see in the journeyman's exam, you'll be able to confidently get 100%. There is another version of the voltage drop formula, but to me, that one's a little bit more confusing. I always found this one, excuse me, to be quite simple, easy to remember, and that's what we like, right? That's what we want as electricians. Easy, factual, accurate, and useful for us, right? So that's your voltage drop, right? And so see if there's anything else. Oh, let's go over that example from the it was this one here. All right, so right here, 20 amps, 300 feet. They're using size number 12, and the circuit is 208. So let's go ahead and change the parameters on this example and we'll work through it. So right here, since it's 208, that's going to be a three-phase system. So I'll show you guys what changes for that. I'm going to erase this stuff here. Keep that and erase all this. Okay, the rest stays the same. So right here, the distance is, I believe it was 300 feet. Yeah, 300 feet. Our voltage is 208. Our ampacity required for the load is going to be 20 amps. And I think that's pretty much it, right? They didn't specify if it's copper. But if it doesn't say what type of wire, excuse me, if it's aluminum or a copper, assume that it's copper, right? Again, it has to specifically say it's aluminum for it to be aluminum. If it doesn't, assume it's just copper, right? So right here, the 3 watts at 3 lamps at 1,000. So if you were to, if you multiply 3 times 1,000, you get 3,000. If you divide that by the 208, it should give you your amperage, 14. So not quite accurate there, but let's say it's 20 amps. Maybe they have some other stuff on there too, sensors or something, a little bit extra. But let's go off of the 20 amp and size number 12, right? That's what they're saying. Like, all right, will size number 12 work for this example? So we'll go with size number 12 for right now, which again, size 12 would work typically for a 20 amp circuit. Well, because of that really long distance, I don't think it's not going to work. So right here, we're going to replace this formula with the numbers now that we have, right? 2 stays just 2 times copper, which is going to be 12.9, 12.9 times the amperage now is going to be 20, and the length is now going to be 300 feet. 300 feet. And we're saying that we're going to try to use size number 12. Size number 12, the cm for that is 6,530 over 6530. Okay, so now we'll do our math, right? We'll go ahead and 2 times 12.9 times 20 times 300. 154,800 divided by 6530, which is our CM for size number 12, right? It's going to give us a total voltage drop of 23 volts. It's a lot, right? How to calculate 3% of 208. So you go here and say 208 times 0.03. Right, the 0.03 is very important. So we can only drop 6.24 volts, and we're dropping 23. So definitely size number 12 will not work. It's way too small. So we're going to have to definitely go up in size to find something that would work with this distance. So right here, we're going to say, okay, none of this worked. I'm going to erase some of this stuff, erase, and number 12 didn't work. So now, because it's such a big difference, right? 24 volts, and we can only drop 6 volts. We're going to skip a couple of wire sizes up because 10 was most likely not going to work. 8, I don't know if 8 would work either. Let's go off of number 6. Let's see what number 6 will give us, right? Number 6, the CM is 26,240. So all that stays the same, 26,240. And we'll go in 2 times 12.9 times 20 times 300 equals divided by 26,240. Okay, that would work. Right, and again, where I got this numbers, because first we started with 12, and that was just way too much voltage drop. So I said, okay, 10 probably is not going to work because, again, it's such a big voltage drop. And we also skipped number 8 because we're like, well, maybe not even number 8 because it was a pretty big voltage drop on size number 12. So we said, all right, number 6 gauge, which has a CM of 26,240. That's what we popped in here. So when we did that, we ended up with 5.8. You can call this 5.9. You can even call it 6 volts. Right, so, and how much voltage were we allowed to drop? Again, how to calculate that is from your source, in this case 208 times 0.03. So we're good. We're dropping 6 volts, and we're allowed to drop 6.625 volts. We're fine. Right, that quarter voltage difference isn't going to really be a big deal, right? As long as we're not over that, we're fine. So right there, and so we ended up going from size number 12 wire, which originally would work if there wasn't such a long distance issue. Because of the 300 feet, we went from size number 12 all the way to size number 6 because of that long distance. So that means if you don't plan this out properly, and you're like, all right, size number 12, 20 amps, yeah, no problem. I didn't pay attention to school. We're going to install half-inch EMT, save money. We're installed size number 12 THHN. Boom, you install this. You dig the trench. You put the conduit. You pull the wire. You connect these lights together, and the lights don't turn on. And you're like, the breaker's fine. The wire pull is fine. The source is fine. My connections are fine. Why are the lights not working? You come and check your voltage with the voltmeter. You only get, what was it? 24 volts. So if you subtract 208 minus 24, only giving the lights 184 volts, right? Which is quite a bit. So and then percentage wise, that's going to be, to get that is you divide 208 by 184. Oops. What happened to my calculator? There it is. 208 divided by 184. So is that right? No, it's I think 184 divided by 208. 184 divided by 208. No, that's not right. I'm trying to get the percentage of how much we're actually dropping. It should have been 208 divided by 184. My calculator keeps disappearing. 208 divided by 184. It's definitely not 1%. It was a lot more, right? Because it was 24. I can't would it be 208 and we're dropping regardless of what it is, it's way more than 3%, right? Because 3% again is 208 times 0.03. So only 6.24 volts are allowed to be dropped. Anything more than that is going to be exceeding that 3%. And so again, we are just dropping 6, so that's barely enough to make it, right? So that's how you calculate voltage drop, right? When it comes to stuff like where it's such a close call, let's say that you make your calculations and the light or the motor manufacturer says, oh, you're only really allowed to drop 5.8 volts, and you calculations come out to 6 volts exactly. Like what happens when you get into the minuscule stuff? So what I would do as a contractor or electrician or journeyman, not as an ET because that's kind of above your experience initially, right? For sure as a journeyman and definitely as a contractor, which some of you guys are, might be interested in pursuing. When it comes so close where you're like, damn, it's only a couple of volts or a volt or two, is that going to work? What you want to do is call the manufacturer of that equipment, of that motor, of those lights, and say, look, this is my situation, right? Because they have a support team, right? They want things to be installed correctly. They want their product to work correctly. So they'll definitely provide support to electricians in these questions, right? And they're the ones that are going to absolutely let us know, like, will one volt or 2 volts make a difference? Will this operate? Right? And they're gonna know. They're gonna know, like, oh, on this situation, if you have 1 volt over or half a volt over, it's fine, right? After you tell them, look, I did my calculations. This is my voltage drop. This is my piece of equipment. This is the serial number for that equipment. These are my numbers. Will it work? And they're going to tell you yes or no. And I would even go as further to say, like, hey, can you send me an email, right? Just to get some documentation. Because then if they're telling you, yeah, it's going to work, and it ends up not working, then you can always say, look, I consulted with the manufacturer, and through this email or text or something, I showed them the situation. I showed them the voltage drop. I showed them my math for it, the formula, and these are my numbers. And I asked if it was okay, and they said it was okay. So then the blame, basically, if that doesn't work, would not be on the contractor anymore, because the contractor is doing their due diligence to make sure that, given that situation, it will work, right? And you can say, like, look, I could go the next wire size up, but will 1 or 2 volts make a difference? Because the cost difference will be really big, right? And you can have that information and then tell the customer, look, originally it was this, but because of this situation, we're gonna have to pick a bigger size wire up. Like, let's say that the manufacturer says, nope, you have to be completely strict within those parameters, and even 1 volt extra shouldn't be allowed. So then you say, all right, send that documentation to me, and then you can go to the customer, look, I have to pick a bigger size wire, bigger size conduit, and it's going to be more expensive because of this equipment, right? And so then the blame's not on you. At least you're doing your due diligence in covering yourself, right? And not ignoring it. Because if you just, again, install and it doesn't work, the customer doesn't know voltage drop, right? Regular people don't understand or even care about voltage drop. They just want the thing to work. If the thing doesn't work, or if it works for some time and it burns out quickly, or or malfunctions, that's on the contractor, that's on the electrician. Not on the ET, of course. You as an ET are never going to be asked to handle something like this. But as a journeyman, yes. And absolutely as like a foreman or a contractor, right? If you have your own business, because you're the one that's charging, that making contracts, making the big bucks. And so you have to be aware of these sorts of things. And that's what contractors are aware. That's why you have to first be a journeyman, and it takes time and study and effort to become a journeyman. And then after a journeyman, again, you have to have some experience as a journeyman to then become a contractor. But all those things are what plays into the knowledge and the overall picture of being an electrician, a licensed electrician, right? Certified electrician is a journeyman. A licensed electrician is somebody that owns their business, right? Has a permit. And again, to be licensed, you have to take tests. It's rather difficult. It's a lot of studying, a lot of personal investment because of all these things that play into it, right? And you will see for sure these voltage drop questions on your journeymans and on your C10 exam. So that's pretty much the gist of it, guys. Almost 8 o'clock. And so right here, yep, to answer this one, size number 12 is not enough. It's too small. We ended up settling for size number 4, I believe, right? Size number 4, which is, yep, size number 4. So as you can see, it makes a big difference between size number 12 and size number 4, because then you have to put a bigger conduit, different, basically it's the conduit, right? So yeah, that's a mistake that can be overlooked by many electricians, but as you can see, it's fairly important, right? So all right, guys, we won't have time for the rest of the stuff. This is pretty much the end of this module. So just once again, last day to turn stuff in. We do not have school Monday, so just remember that. George, I sent you a message on Sora, if you could take a look at it real quick. I am finishing almost grading. I think I'll be done within like an hour or so. And I'll reach out to you guys if you're like in danger, if something's your hours or your grades or everything. But I'll basically be catching up pretty soon on the grading, and then tomorrow I'll be finished 100%. And again, if you're kind of in danger, your hours or your grade, I'll be reaching out to you, whether text, most likely text. So just be on the lookout, but just try to turn in as much homework today as possible. Tonight at midnight, you guys are closed off and you have no more chances to turn stuff in. I'll still have, like a couple days to grade, but you guys won't have any more opportunity to turn stuff in. So take advantage. It's 8 o'clock, so you have basically 4 more hours to turn stuff in. Main thing is discussion board, unit exams. Those are attendance. And then, trade terms, review questions, all those things that are kind of worth a lot of points. All right, guys. So any questions for me about anything?
No, sir, not that I have.
All righty. All righty, guys. Well, if you guys are good, then you're good to go. Thank you for hanging on. Have yourselves a great weekend. Tuesday, we have is it the Tuesday, is it our online or no, Tuesdays are online?
Online, yeah.
Yep, Tuesday's online, and Wednesday we'll have a lab. All right, so we'll be in the same room and we'll start a commercial and a bunch of new stuff that we'll learn. All right, guys?
That's the metal cubicles, right?
It's the metal cubicles, yes. Yep.
Okay.
Mm-hmm.
Yeah.
All righty, guys. Thank you so much. Have a great night and great weekend. I'll see you guys on Tuesday on Zoom and see you Wednesday in lab.
All righty. Have a good weekend
Thanks,
yourself,
guys.
man. Peace.
As well. Thank you. Bye, guys.
Have a good weekend. Take care.
Thank you.